Ether channels do give us load balancing, which we love, but it is not absolute to the percentage point pure load balancing. What I mean by that, let's take our lab right now, for instance. We have 4 parallel links in our Ether channel, but that doesn't mean that each link is carrying exactly 25% of the load. What we really have here is load distribution. And what I mean by that is that flows, traffic flows that go from, say, point A to point B, address 1 to address 2, I should say, that's always going to go over the same link in the Ether channel. It's not like if 10.111 is sending data to 100.111, just pulling those addresses out of the sky, that the flows are going to be broken, that the flow from 10.111 is going to be broken up and sent over all 4 trunks in our Ether channel right now, all 4 links. It doesn't work that way. Basically what happens is a CISCO proprietary hash algorithm is run, and it delivers a value of 0 through 7. And what that does, that covers each one of our possible Ether channel links. 0 through 7 actually covers 8 values. And those values are assigned to links in the Ether channel. And it's these values that are actually used to determine which link handles which traffic flow. And again, as a quick reminder, we are dealing with per flow balancing here, not per packet or per frame. Now that algorithm can use any of these values. It can use the source IP address, the destination IP address, both the source and destination IP address, both the source and destination MAC address, or TCP and UDP port numbers. Now, what I'm going to tell you next is one of these things that sounds complicated when you hear it or you read about it, but then you do it and you go, oh, there was nothing to that. And it's a skill we don't get a lot of practice of, so for the exam, I think we should pay a little more attention to it. Because what the switch can do to actually choose the link in the Ether channel that will carry this particular traffic flow, it may use the hash of the last low order bits in the address, the ones all the way to the right, to choose the link, or it can get an XOR involved, an exclusive OR operation. Now, the only time the XOR operation is used for this is when one of the combination load balancing methods is used. You know, source and destination IP address, source and destination port number, source and destination MAC address. You get the point. And now, for every method that involves only one value, the hash of the bits reveals the port or the link that's going to handle traffic for that particular flow. Again, if this bounces off your head a little bit the first time around, don't feel bad. It happens to everybody. But once you see it in action, you do it once on a piece of paper, you'll see how easy it is. Now, the XOR's operation, that even sounds scary. Anything with an X in it, it's like, I don't know if I want to do that. But it's the easiest operation you'll ever carry out. All the stuff you learned as far as binary and subnetting, hopefully for me, for your CCNA studies, it's child's play compared to that. And even that's easy to you now. It's a bit-by-bit comparison. That's all it is. And there are only 2 possible answers, which we love. If the compared bits are the same, the result of the XOR is 0. If the compared bits are different, the result is 1. That's it. Now, the number of bits needed for the XOR depends on how many links we have in our Ether channel. If we have 2 links in the Ether channel, we just need 1 lowest order bit, the lowest order bit possible. Because with 2 links, how many links do we have? Then how many values do we need? We only need 2, and that would be 0 or 1. With 4 links, we need 2 lowest order bits to XOR, because the possible results there will be 0, 1, 2, and 3, and we need 2 bits to express a couple of those values. You see what I'm saying? And then with 8 links, we would need 3 lowest order bits, because the possible results there will be 0 through 7, and to express the highest value there, 7, we have to have 3 bits. And let's do an example of this. You'll see how easy it is. And we're going to use our 4-link Ether channel, and we're going to figure out which one of those links, 0, 1, 2, or 3, is going to carry traffic sourced from 179.38.47.11 and destined for 210.49.39.22. Now, if you want to break down the entire address for practice, that's a great idea. But again, with the 4-link Ether channel, we only need the last 2 bits, because the only possible results we're interested in are 0, 1, 2, and 3. So we only need 2 bits to express any of those. And all you have to do is look at the last octet of each address and look at the 2 lowest order bits. And with 11 in a binary string, we're looking at 00001011 because that gives us the 8, 2, and 1 bits set. That gives us a total of 11. 22 is 00010110. So what bits do we have set there? We have the 16-bit set, the 4, and the 2. You add those up, it's 22. Now, when you have more than 1 bit to compare, we do the XOR on a bit-by-bit basis. So from left to right, the first thing we do is XOR the 7th bit of each octet. Well, that's 1 for each octet. The 7th bit is set to 1 each time. That gives us a 0 for the first bit of the actual XOR result. When we XOR the 8th bit of each octet, we have a 1 and we have a 0. So the return is a 1 for the XOR's second and final bit. So our overall XOR result in that way is 0, 1. Well, what does that convert to in decimal? 1. So the switch will use the port assigned value 0, 1 or 1 to send that data. That's all there is to it. Let's walk through another example, and we're going to use a source IP of 179.38.47.11 and a destination of 190.49.39.15. And with our 4-bit path EC, our 4-path EC, we need the last 2 bits of each address for the XOR. We break down 11, 00001011. That gives us our 8, 2, and 1 bit set. 15, we know everything after that 16-bit is going to be set 8, 4, 2, and 1. Both bits in the 7th position are 1s, so that gives us a 0 for the XOR returns first bit. The 8th bit in each position, the 8th bit in each, let's try that again. The 8th bit of each one of those is a 1, so they match. So our XOR overall return is 0, 0, and that means the link assigned value 0 is the winner. That's the one that's going to be taking data from 179.38.47.11 to 190.49.39.15. Again, very important to note that when everything remains the same as far as your addressing goes, address flows from A to B are always going to go over the same link in the Ether channel. That's all there is to it. It takes a little bit of practice, and that's, again, all there is to it. I'm going to show you how to change that and check in just a moment. But I know what a couple of you are thinking about, and I want to go back to this table. I would say this is off the record, but I have a microphone hanging 6 inches from my head. So I really can't say that, but this is away from the exam. I know you look at this and say, well, that's great, but what about Ether channels that don't have 2, 4, or 8 links? Okay, speaking real world here and away from the exam theory, it was held for a long time, and for good reason really, that Ether channels should always have a number of links equivalent to a power of 2, which is a fancy way of saying you should either have 2, 4, or 8 links in your Ether channel. And some of that had to do with load balancing and load distribution. And the thing is, when you add odd numbers of links in there, or you have odd numbers like 3 or 5 or 7, your load balancing can get a little unpredictable and a little out of whack. I realize that's a really technical term, but it was something to be avoided. People have really gotten away from that thinking, and I've heard more people say, well, yeah, I have 3 links in an Ether channel at work, blah, blah, it's no problem. It really depends on how much balancing you're doing, how many hosts you're doing. There's no one-size-fits-all answer to that question. But I just want to tell you, in the real world, you are liable to see Ether channels that have 3 links or 5 or 7. It can play a little bit of havoc with your load balancing, which is why in the CCNP switch exam, it's really out of the scope of the exam. We're not going that far with this. This is probably more than you need that I'm already giving you. But I just want you to know that in the real world, you may well see Ether channels that have non-power of 2 number of links. And they work just fine. But let's just stick with that 2, 4, and 8 here for the XOR. And let me go and bring up the live equipment. Show you a couple things here, because the defaults as far as load balancing configuration that differs, and your exam is not going to get into switch models. It's not going to say, well, on the CISCO 3560 XL42, what's the default Etherchannel load balancing config. But I do want you to know, first off, that you can see that anytime you want to with Show Etherchannel Load Balance. And it's just going to give you that information right there. And it's also going to tell you your load balancing addresses used per protocol, non-IP, IP version 4, and IP version 6. We're not going to get into each one of those individual ones in this video. But again, this shows you exactly what your load balancing scheme is right now. If you wanted to change that, then you can do that with the port channel load balance command. And you'll notice this is not a per port deal. This is global. This is for your entire switch. And notice that the two options here listed that are more than one, it's going to use the source and the source and destination IP and MAC addresses. That even mentions XOR in the middle of it. So that's a good way to remember it as well, that when you have more than one value, the XOR does get involved. And really, that's all there is to it. You just do a source dist IP, and then you can just run your Show Etherchannel Load Balance command again, and you can see that successfully changed to source and destination IP address. That is really it for the XOR operation and for the way loads are distributed via your Ether channels. One more thing I wanted to show you, and it's something, we're going back to spanning commands. Oh no! Let's go to switch 3. Now, we have looked at this quite a bit over the last couple of hours, and I'm sure you noticed at one point there was something here about an Ether channel. Spanning tree Ether channel specific configuration. We better find out what that is. Ether channel, we're guarding something, and we're enabling the guard to protect against Ether channel misconfiguration. Okay, and okay, that seems to cover a lot of territory. The full command is spanning Ether channel guard misconfig, and there's really there are no other options to that. And what I wanted to tell you about it was, if you use one of the Ether channel negotiation protocols, you really should not run into an issue with a misconfigured Ether channel, because of course it wouldn't be created in the first place if there was a problem. But the channel group on option that I used in the first Ether channel we created, that sidesteps negotiation entirely. And again, a lot of production networks don't like that option. They want to use one of the negotiation protocols. But you could run into trouble with the on option, say if one side of your links is set up for an EC and the other side isn't. I speak from experience there. I've seen that happen. Well, to prevent the creation of a switching loop due to Ether channel misconfiguration, you can run that command. And again, let me give you the full command. It's spanning Ether channel guard misconfig. As a result, if a condition exists that might result in a switching loop, the ports are placed into error disabled state immediately. So if you start seeing something else about error disabled ports when you're building an Ether channel, there is a very good chance, an excellent chance, that this particular feature has been enabled. But again, no options, it's all or nothing. And I've said it a couple times in this video, but that's really all there is to that particular feature. That also wraps up our look at Ether channels. We've built them, we've negotiated them, we've seen how a particular flow of traffic is going to be distributed over the trunks, over the links, and how that link is chosen. So in the very next section, I believe we are going to start getting into some layer 3 switching, and I will see you in the very next section.